All right. In this section, in 3.3, it's entitled Parent Functions and Piecewise Functions. These are like the basics. Okay, so if you're ever going to deal with functions, if you're going to do well in 1050, if you're going to do well in the rest of this class and that sort of thing, these are like the fundamental building blocks of functions. So if you understand what these functions look like, and more importantly, why they look the way they do, because some of these you're already going to be familiar with, but what we want to be aware of is, why do these things make the particular shapes that they do? Okay? So as we go through here, if you'd keep that in mind, we're not just trying to figure out, well, what does this particular shape look like? We want to know, why does it look like that? Why does it have the shape that it does? Okay, so keep that in mind. The other thing is, don't be surprised. Hopefully we're going to get done with all of this today. Don't be surprised if tomorrow I hand you a sheet that looks something like this, and then just say, hey, this is a quiz, make these graphs. Okay, because this section is really easy. We're basically going to go over all the homework right now. Okay, you've got some matching problems and stuff like that. It's pretty easy to do. Okay, but again, more importantly, you want to understand why each function makes the shape that it does. Okay? All right. So just as a reminder, when that function makes the shape, the graph is a picture of all the points that work in the equation. So remember, if the point works in the equation, then it's on the graph. If it's on the graph, then it works in the equation. Okay, so the first one we're going to go over is called the constant function. Okay, so the example that I've got here is f of x equals b. Well, b represents a number. Okay, and remember, y is the same as f of x, so this would be y equals a number. Okay, so let's do a specific example. Let's say I've got y equals 2. Or again, we could write that as f of x equals 2. Now, we went over last week, if you have y equals a number, or f of x equals a number, what type of function is it? What does it look like? Yeah, it's a linear function. It's a, what is it, John? Horizontal. It's a horizontal line. So this would be a horizontal line at y equals 2. So it doesn't matter what we plug in for x. In fact, there's no x in here to plug in. So no matter where we go on the x-axis, I can go to 5, I have to go up to 2. I can go to -3, I have to go up to 2. If I stay at 0, I have to go up to 2. No matter where I go, to the left or to the right, I always get exactly the same function value. On this particular one, I get 2. So that, again, no matter where I go on the x-axis, that implies that the domain for this type of function is -infinity to infinity. It's all real numbers. Okay, now on this particular one, what would the range be? Don't write it down, but what would the range be on this particular one? It would only be 2. Because if I take this graph and I squish it onto the x-axis, or excuse me, the y-axis, and squish it onto the y-axis, the only thing that would be covered would just be 2. Okay, now in general, the function is, or the horizontal line is, wherever b is. So if b is 2, it's right here. If it's 7, it's up here. If it's -5, it's down here. So the range would be whatever b is. Does that make sense? Okay. All right. So next we're going to talk about the identity function. So the identity function is one that you're already familiar with. So if we were to write it in terms of y, it would just be y equals x. It's a linear function. What's the slope of that line? It's 1. What's the y-intercept? Y-intercept is 0. Okay? So we already know how to graph it, but I'd like you to think of it in a little bit different terms. This is why it's called the identity function. Okay? All of you have an identity. You're your own person. So what this does is, whenever you plug a number into it, it maintains its identity. It stays exactly the same. So if I plug in a 0, this function spits out a 0. If I plug in a 1, it spits out a 1. If I plug in a 5, it spits out a 5. If I put in a -2, it gives me a -2. So that function looks like this. This is the identity function. It's just a line, perfect 45. And we'll call it the identity function. So, I mean, that's kind of a complicated way to talk about a line with a slope of 1 that goes through the origin. Okay, but that's the way it is. We call that the identity function. So if somebody says that, you just say, oh, they're just talking about that kind of the parent graph of all lines. Okay, that's what it looks like. Okay, so what's the domain? What can you plug into this function? Anything you want, right? And you know that because it doesn't have any one of those three issues. What are those three domain issues again? Okay, can't take the even root of a negative, can't divide by 0, and can't take log of a negative or 0. So if it doesn't have any division, even roots, or logs, we know we're probably in pretty good shape, at least for now. So the domain is from negative infinity to infinity. You can plug in anything you want. And what about the range? What if we take these points and we squish them onto the y-axis? What part of the y-axis would be covered? The whole thing, right? So how would we indicate that? We'd just say from negative infinity to infinity, or we could say all reals if you want. Okay. Again, function notation, or excuse me, interval notation is generally preferred. Okay. All right. Any questions? Okay. You all know what this one looks like. We call it a parabola. That's the shape that it makes. We call that the squaring function. Both of these are power functions. So again, it's important to think about why they make the shapes they do. When you plug in a 0, it just squares 0 and you get 0. When you plug in a 1, you square 1, you get 1. Plug in a 2, you square 2, you get 4. If you were to plug in a 3, you'd get 3 squared, which is 9. And the reason this other side looks exactly the same, or in other words, the reason this is an even function, is because when you go to the left of 0, so when you go to negative 1, when you square that, you get the same thing as if you went to the right 1 unit. Okay, so we talked about symmetry the other day. So it looks something like this. There's what the graph looks like, and this is the parent graph, and you'd want to have those shapes, those points memorized. Okay, so you'd want to know that the vertex is at 0, 0, that it goes through 1, 1, 2, 4, negative 1, 1, and negative 2, 4. We'll call those like the 5 key points. If you've got those basic shapes there, that's where the bend on this graph happens. That's where the major action is. So you'd want to know what those 5 points are. Do we have any division? Nope. Any even roots? Nope. Any logarithms? Nope. So do we have any domain issues? Nope. So you can plug in anything you want. So the domain would be from negative infinity to infinity. Okay, now the range on this one is different than the other ones we've come across. When you plug something in, the smallest number you could possibly get would be 0. That happens when you plug in 0. For any other number, whether you're plugging in a small or a big positive or a small or a big negative, you always get out a positive, so the domain would be from 0 to infinity. And Charles, round or square around the 0? It is square. It's square because it actually comes down here and it touches 0 just once. Okay? All right. Any questions? Okay. The cubing function is different. Cubing function is different. This one, when you plug a number in, it squares it, it always turns out to be positive. When you cube something, if it was negative to begin with, you're going to have 3 negatives. So the answer is going to be negative. If it's positive, you're going to have 3 positives, so it's still going to be positive. Okay, so for 0 on the cubing function, you plug in a 0, it cubes 0 and gives you 0. When you plug in a 1, it cubes 1 and gives you 1. When you plug in a 2, it cubes 2 and you get 8. So this point right here is 2, 8. This one is 1, 1. And then on the other side, when you plug in a negative 1, you get out a negative 1 because there were those 3 negatives, remember. And when you plug in a negative 2, you get out a negative 8, again because there were those 3 negatives. So the graph looks something like this. Okay, and just like on the parabola, okay, this doesn't have a special name like that one does. This is just a cubing function. Okay, it looks like this. That has 5 key points. And you'd want to know what those are. Because just like with a parabola, everybody here was in 1010? You know how with a parabola we slid it left, right, up, down, stretched it, and shrunk it, and all that sort of stuff? We're going to do the same thing with these. So if you know what these 5 key points are, you're in good shape. Okay? No division, no logarithms, no even roots. What's the domain? All reals, negative infinity to infinity. Okay? Or you can take the graph and squish it onto the x-axis. If you squish it onto the y-axis to figure out the range, You can get out as big a negative or as big a positive as you want, and any number in between, so it's also negative infinity to infinity. Okay? Any questions? Okay, so what we've got so far are the constant function, the identity function, the squaring function, and the cubing function. Now we're going to look at some that are a little bit different. You may have seen these before, but you may not have. So this one is the square root function. Okay, now, on the first 4 examples, we didn't have any domain issues. No division, no even roots, no logarithms. Here we've got an even root. What is not going to be okay to plug in here? Okay, I heard a bunch of people say negative. I heard a couple zeros out there. Is it okay to take the square root of 0? Yes. That's totally okay. So we can plug in 0. What we can't plug in is a negative. So we're going to start at 0, and any positive would be just fine. So it would be 0 included up to positive infinity. Now, when we take square roots, do we get negative answers out? Nope. Okay. Not with just something as simple as this. So we're looking for the range to be, well, if you plug in a 0, you get a 0. If you plug in a 1, what's the square root of 1? 1. Square root of 1 is 1. What's the next most convenient point to plug in? 4, because 4 has a nice square root, right? So this point would be 4, 2. So we're going to want to know those. This is 0, 0. This is 1, 1. This is 4, 2. After that, you don't have to know this, but after that, what would the next most convenient point be after 4? 9 would work. 16, 25, because those are all perfect squares, right? So this is 4, 2, and it looks like this. If you had to describe this, by the way, the range is from 0 to infinity also. If you had to describe that, what does it look like? Yep, half of a parabola flipped over. Okay, it's the top half of a sideways parabola. That's exactly what it is. And notice what we've got here. Look at these points. 0, 0, 1, 1, and 2, 4. Okay, these are just kind of like the x's and y's have been switched. Okay, we'll talk more about that when we get to inverses. Okay, but that is exactly what it is. It's the top half of a sideways parabola. Okay, any questions? Okay, so let's do the cube root function. That's an odd root, right? Any problems taking odd roots? Nope. Can you take the odd root of a negative? Yep, that's fine. So we shouldn't have any domain issues. So we suspect that the domain is going to be negative infinity to infinity, but let's look at the graph and figure this out. If I plug in a 0, what do I get? I get a 0. If I plug in a 1, what is the cube root of 1? Cube root of 1 is 1. Okay, those are nice and easy. Okay, question, don't say anything out loud, just think. After 1, what is the next most convenient point to plug in here to find the cube root? Don't say anything out loud. Might be helpful to look one line up at that one. Shane, what do you think it is? 6. Does 6 have a nice cube root? 8. It's going to be 8. Very good. So the next nicest point to plug in would be 8 because the cube root of 8 is 2. So this point is 8, 2. This point is 1, 1. This one is 0, 0. Now, what happens when we plug in negatives? Let's pick convenient numbers to plug in that are negative. Negative 1 has a nice cube root. It's negative 1. What's the next most convenient point after that? Negative 8. So we'll go to negative 8, and the cube root of negative 8 is negative 2. So the graph looks something like this. And those are the 5 key points that we'd graph there. Yeah?
Does that mean that it continually goes out on the y-axis as well?
It does. Yep, it continues to go up. It doesn't go up very fast, though. Okay, think about this. In order to get up to 3, how far do you have to go out on the x-axis? 27. In order to get up to 4, you've got to go out to 64. So it doesn't grow very quickly, but it does continue to go up, and it does continue to go down. Now, we've kind of already talked about the fact that you can plug anything you want in here, so the domain should be negative infinity to infinity. And the range If it continues to go down and continues to go up, what part of the y-axis would be covered if we squished all these points together? All of it. So this would be negative infinity to infinity. Okay? What type of symmetry does this have? Symmetry with the origin. Okay? If it's symmetric with the origin, we have a quick three-letter word that describes what that is. Symmetric with the origin is odd. Symmetric with the origin is odd. So if somebody says, hey, I've got an odd function, we know it's symmetric with the origin. So you'll notice that that one is symmetric with the origin. This one's symmetric with the origin, it's odd. This is symmetric with the origin, it's odd. This one is symmetric with the y-axis, so it's an even function. Okay? All right. Any questions? Does that seem pretty easy so far? Yeah. Does the square root, well, is it symmetric with the origin? No, so it's not odd. Is it symmetric with the y-axis? Nope, so it's not even, so that would be neither. Okay? Good question. Okay, so if we flip this over, on the other side, we've got the reciprocal function first. So the reciprocal function. What does the word reciprocal mean? Okay, not quite opposite. Opposite would be negative. Means flip it over, okay? So what this does is it takes a number and it flips it over, okay? So let's just talk theory here for just a second. What happens if you take a big number? So pick a big number. If you take a big number like 57 and you flip it over, what do you get? 1/57th. So the reciprocal function takes big numbers and it makes them small. Okay, now pick a small number. Okay, pick a fraction. Okay, as much as you don't like fractions, they're actually really useful, especially here. Pick a fraction between 0 and 1. Alyssa, what'd you pick? 1/6. What happens when you take 1/6 and you flip it over? Okay, it makes 6. Okay, anybody pick a smaller fraction than 1/6? 1/32. What happens when you flip 1/32 over? You get 32. So the reciprocal function, this is what it does. Reciprocals flip things over. Reciprocals take big numbers and it makes them small. It takes small numbers and it makes them big. Does that make sense? So if I were to plug in a 1, well, that's the one number that when you flip it over, what happens to it? Stays exactly the same. Okay, so I get a 1 out of that. I'm going to actually label that point right there. If I pick a 6, 1/6. If I pick a 9, 1/9. So it just continues to get smaller and smaller and smaller, so it looks like this. But what happens if I pick a small number like 1/2? 1/2 is, flip it over, it's 2. If I pick 1/10, so I'm just right here, 1/10, I'd have to go all the way up here to 10. What if I pick 1/1,000th? So I'm right over on the right side of the y-axis by just 1/1,000th. How far up would I have to go to get to the point? Flip over 1/1,000th, I get 1,000,000. I'd have to go way up here to 1,000,000. So what this graph looks like is this right here. It's got a little curve to it right there, but that's what it looks like. That is the reciprocal function. And again, what it's done is, everybody watch please. I'm going to blow this up just a tad. It takes these small numbers between 0 and 1 and makes them really huge. It takes these big numbers that are bigger than 1 and makes them really small. That is their function value. Okay, good? Okay. Do I have any division in this function? Yep, so I got to be careful. What thing can I not flip over? 0. I can't do this. So 0 is 0/1. If I do the reciprocal of that, if I flip it over, I get 1/0. Or really what I do is I do this. 1/0/1, flip that over. Okay, so that's not defined. So there is no function value at 0. Okay, that's not allowed. I don't have a value right here. Okay, so I get to skip over that. But let's see if we can get this. These are small negative numbers. What do you get when you flip over a small negative number? You get a big negative number. So if you take -1/2 and you flip it over, you get -2. If you take -1/20th and flip it over, you get -20. So you get these huge negative numbers here. By the way, what happens if you flip over -1? Still -1. Okay, it's the one number. Remember, 1, whether you do the reciprocal or not, it's still the same thing. So it looks like this over here. And these are big negative numbers. What's the reciprocal of a big negative number? Small negative number. So let's take -5. Flip it over, you'd get 1/5. Let's take -9. Flip it over, you'd have -1/9. So does this ever come up here? Does it ever hit the x-axis? It never does. It never hits 0. It's always negative. So it looks like this. Okay? So here's what our graph looks like. That's what it looks like. Domain. What did we say we could not plug in? What's the only thing we can't plug in? Okay. So we could write, you can plug in anything you want, -infinity to infinity, except for 0. Or if you just wrote x not equal to 0, that would be okay. That's not the end of the world. Okay, so it would be all right if you just wrote that. So if I take this graph and I start squishing these points onto the y-axis, what part of the y-axis is covered? Everything but 0, right? Because on this side it comes down and it comes down but never touches the y-axis. And then same thing over here. On this side it comes up and it gets really close to the x-axis. Gets really close to the x-axis, but it never actually touches it. Okay? So this is going to be -infinity to infinity, except for y is not equal to 0. Okay? And again, you could put just this if you wanted. Okay? Any questions there? Does that make sense as to why it makes the shape it does? Okay, really, really important that you think about that. It's going to come up again in just a second. Okay, does anybody want to come up here and graph the absolute value function for us? Shane? Just be careful not to push the button on the side. Okay, so what's the first number you're going to plug in?
Up at the origin.
Yep. If you plug in a 0, yeah, don't hold it there too long. Okay.
All right.
If you plug in a 0, you get a 0. Absolute value of 0 is 0.
All right. So then, let's plug in +1. If you put in +1 for x, you get out +1 for y. Right.
Mm-hmm.
And so, really, with any number you could put in, like you put in 5, you get out 5. So it'd be 5, 5.
So it kind of looks like the identity function, right?
Yeah. Except now, when we get into negatives, because it's an absolute value, you put in -1, you'd still get out a +1. And if you put in a -5, you'd still get out a +5. So instead of that, just that straight line or a parabola, you get a nice V shape.
Very good. Okay,
That's really
excellent.
bad.
Nice job. Nope, that's it. So notice again, we don't have any logarithms, we don't have any division, we don't have any even roots. So the domain is going to be -infinity to infinity. You can see that on the graph. You can plug in anything you want. Okay. What about the range? Okay, range is 0 to infinity. Because we don't have any negative values, because it's absolute value, it refers to the distance from 0, and that's always positive. Okay, and 0 is included because it does come down here and actually touch right there. So it's just like a perfect 45-degree angle coming in and a perfect 45-degree angle going out. Okay, any questions there? Sure? Okay, anybody want to try this next one? The reciprocal square function. You want to try it?
Sure.
Okay. So reciprocal is going to flip things over, right? It's going to make big numbers small and small numbers big. What's squaring going to do to everything?
Make them even bigger.
Make it bigger and smaller. And what does squaring always do? It always turns things into positives. Okay. So think about that.
So this one, you had that negative side, right? So this means that, so let's plug in 1, and 1 squared is 1, so that'll always be a 1.
Okay, so
And then,
plug in a 1, you get 1 squared on the bottom, 1 over 1 is 1, yep.
right. So then if you plug in a 2, then that squares it, and that's 4. So
Go
so that
to
would
2, and so it would be 2 over 2
Right.
and up 1/4. So we'd barely go above.
right,
Yep.
so it'd be like that. That's annoying. Okay, so so that just kind of continues out, right? So I mean, if you do like 3, then that'll be like 1/9.
Mhm.
So it just
Okay.
continues like that.
It takes big numbers and they get small, but they get small really, really fast, right? Faster than they did before.
Yeah. So and then the other way around, it'll go. So if you did 1/2,
Mhm.
and I'm not exactly sure about this part.
So if we plugged in a 1/2, this would be 1 over 1/2 squared. So this would be 1 over 1/4. What's 1 over 1/4? Flip that over, that would be 4 over 1, so it would be 4. So we'd go to 1/2 and we'd go up here. So it takes the small numbers and makes them big, but it makes them big even faster. Okay?
So that would end up looking like this. Right? Or kind of like that.
Kind of like that.
Yeah, that sucks really bad.
I wasn't going to say anything.
Okay, so then that means that the other side is kind of like this one. I think it does the same thing, so it does. So you plug in a -1. That'll still come out to be a -1, but it makes the x positive.
The Y positive.
Or,
Yep.
yeah, the y, my bad.
Takes a while to get used to that pen.
And then, so basically just the same thing, just gets continually smaller on that side, and then this side gets bigger. But it always flips the y over to make it positive.
Make sure it's positive. I know I'm going to pick on John. If it does the same thing on both sides should look the same, right? Do his sides look the same? No, but it's the right idea. Okay, that's fine. I mean, he got it right. What type of function would this be? Because it's symmetric with the y-axis. It's an even function. Okay, does that make sense? Okay, so the graph should look, and this dipped below here. If we square something, if we take a number and we square it, it's always going to be positive. So it's going to look something like this. Okay, not really a corner to it there, but it's going to run along here. And then the other side is going to look exactly the same. Now let me show you another reason why it's got to look the same on both sides. This is 1 over x squared. Isn't that the same thing? Couldn't I write it that way? So this is the reciprocal graph that we were looking at up above. It's that guy right there, but everything is just squared. So this branch that's down here, it would be made positive, and it's going to be up there. Okay, and the small points are made even smaller, because what happens when you square a small number like 1/10 times 1/10? You get 100. That gets even smaller. So it's going to be steeper here and flatter here, steeper here and flatter here, but everything's going to be positive. Okay, again, you can't plug in a 0, and you also can't get out a 0, or is it that simple? Because what else don't we get out? We don't get any negatives or zeros. So the range would be from 0 to infinity with a round bracket around 0, because we never actually touch the x-axis. Does that make sense? Okay, 2 more, right? Then that's it. We'll be done before class is even over. Okay, so let's take a look at this one. This is called the greatest integer function. I think this book has it look like this. Some textbooks it looks like this, and some of them refer to it as a floor function. Okay, so I don't want you to write this down. I just want you to watch. Okay. So here's what this means. I'm going to write this work over here just so you get the idea, and then I'll erase it. Okay, if I were doing the greatest integer for 1.5? That's asking a question. What it's asking is, what is the biggest integer that's not bigger than 1.5? What's the biggest integer? What's the biggest whole number that's not bigger than 1.5? 1. If I did 1.9, what's the biggest integer that's not bigger than 1.9? Still 1. If I did 1.99999, 1. The minute I get to 2, what's the biggest integer that's not bigger than 2? 2. And if I did 2.1 and 2.9 and everything, it would always be 2 until I get to 3. So for everything in between, blow this up just a little bit, for everything in between 1 and 2, the answer is 1. But the minute I get to 2, it jumps up to 2. For everything in between 2 and 2.99999, all the way up until 3, it's always 2. And then the minute I get to 3, it jumps up to 3. So what we get is this step function, it's called, for obvious reasons. So where would this one be? What's the greatest integer for 0.5? 0. Okay, so it looks like this. Okay, now here's where people get messed up. Negative 0.5. What's the biggest integer that's not bigger than negative 0.5? Okay, it's either 0 or negative 1. Which is it? It's negative 1. For two reasons. One, it makes sense with the stair-step pattern that it would drop down here to negative 1. And the other thing is, 0 is bigger than negative 0.5. So it just continues to look like this. Okay? That's what the greatest integer function or the floor function looks like. Okay? Okay. Okay, so now the tricky part. We've got to think about this for a second. What's the domain? Sam says it's all reals. Is that right? Any even roots? Nope. Any logarithms? Nope. Any division? Nope. In fact, can you think of a number that's not covered here? So if I were to take this and I were to squish all the points down on the x-axis, okay, that certainly covers everything here, and this point comes down, fills in that hole, and hits 2. So you can plug in anything you want. The domain is from negative infinity to infinity. Now, the range. Take these points and squish them onto, so I wish I could make this smaller. Okay, so I'm just going to do this. I'm going to change to this color right here. I'm going to slide these points over. They cover that point in there. Is there anything that covers these points in between here and here? Nope. So if I take all these points and I squish them onto the y-axis, what points would get covered? Just the whole numbers, or because they're positive and negative including 0, then they would be integers. Okay, so all integers. Any questions? Okay, last one. Okay, this is called a piecewise function, and it's called a piecewise function for a really good reason. It comes in pieces. Guess how many pieces this has? Has 3 pieces. You'll come across piecewise functions that have 2 pieces, 3 pieces, 4 pieces, 8 pieces, whatever it happens to be. Most of the ones in this textbook are anywhere from 2 to 4. They usually don't give you a ton of them. Okay, so this comes in 3 pieces. Okay, now this is just one particular example. You'll have a couple in the textbook. I just made this one up because it's a fairly easy one to get used to. So it's going to come in 3 pieces. So everybody should know, what shape is this? You should know what shape it is. It's also called the identity function. It's this graph right here. Okay? So somewhere it's going to look like this graph right here. So it's going to look like this. But where does it look like that? Right here. Anywhere that's less than or equal to -1 on the x-axis. So here's -1. So this is like the cutoff right here. So I'm not going to do this entire line. I'm just going to do this piece of the line. Okay, there's my first piece. Okay, now, it extends forever in this direction because I can use any value I want that's less than or equal to -1. Once I get to this endpoint right here, do I put an open circle at the end or do I put a closed circle? Which is it? It's going to be closed. Okay, so that's the first piece. Okay, now I'm going to change colors. 2. You should know what shape that is. It has a name. It's the first one we went over. It's a constant function because it just stays constant. It's a horizontal line. Where? At 2. Okay, now, is it the entire line? It can't possibly be. Everybody watch? It can't be because over here it wouldn't pass the vertical line test. It only looks like this horizontal line between here and here. So from -1, so right here's the cutoff, all the way to 0. There's the other cutoff. So I'm going to erase this, and the only part that I'm going to use is just that stuff right there. Okay? Okay, now, at this end point right here, at -1, open or closed circle? Got to be open. You can tell without even looking here. It says it's got to be greater than -1. But if these were both closed, what test wouldn't it pass? Vertical line test. And what about at 0? Okay, it would be closed. So I'll put a closed endpoint there. Okay? And then x squared. Parabola. Okay? Looks like that. But it can't possibly be the whole thing because then it wouldn't pass the vertical line test anywhere over here. So I'm going to erase everything but where it says it looks like that. Where does it look like the parabola? Okay, notice I said where? Anywhere x's are greater than 0. So on the right-hand side. So I'm going to erase all of this. Oops. And I'm going to go like that. Make it look right. And open or closed at this endpoint. Got to be open. Okay? Let me blow this up just a tad. That's what it looks like. Any questions? Yeah.
How is 2 supposed to tell you that it's a constant function? Like, I understand how that x squared shows that it's a parabola, and the x shows that it's the identity, but there's no 2 in the actual, like...
What do you mean?
It says fx equals b, that's like the actual...
Oh!
And that 2 is supposed to tell you that it's a constant function, I just don't understand how
Okay.
that tells you.
So this can be any number we want. Okay, so if this were y equals 2, y equals -5, y equals 7, whatever that number is, that is the constant. Okay?
So the reason it could basically be any number because it's the only thing that's replaceable by any number.
Yeah, I suppose if you wanted to think of that. Are you talking about this one or this guy right here, the last one?
I don't see what you're putting out, sorry.
This one here.
This one. I just was I was confused as to how that 2 showed you this. The constant,
So another way we could do this is we could say y equals x as long as x is less than or equal to -1. Y equals 2 as long as -1 is less than x and less than or equal to 0. And y equals x squared as long as x is greater than 0. Okay, so there's your line. Okay, but it only works right here. There's your parabola, but it only works on this side right here. This is a horizontal line, but it's only a horizontal line. The function is only equal to 2. It's only constant between -1 and 0. Does that make sense?
Yes.
Okay. If you have trouble with that, come and see me. By the way, what would the domain and range be with this? Okay, on this particular one, it's all reals for the domain. You can plug in anything you want. What about the range, though? Take the graph and squish it onto the x-axis. Everything would be covered here. Everything would be covered here, but there's this little gap right here. Okay, let me blow that up. How big is that gap? It's 1 unit. So I can cover everything from negative infinity all the way up to -1. And then where do I start getting answers again? 0, and I go to infinity. Round or square around the 0? Round around the 0. Okay? Because it's not included. Whoop. You're right. Yep, thank you. Thanks for catching me there. Okay? All right. Any questions? Okay, have a great day.
Yeah,